In today's lecture, we're going to begin looking at a new topic dealing with solutions. And first of all, we want to define what a solution is. In Chapter 4, we see that a solution is defined as a homogeneous mixture. Now, remember, in Chapter 1, we defined a compound as being a pure substance versus being a mixture. A chemical compound contains a definite composition. A mixture does not. And a solution then is a homogeneous mixture. By that it means that the physical state of the materials making up the mixture are all the same. So if we're talking about a solid solution, which we can have, then everything in the solution is in the solid physical state. If we talk about a gas solution, like we could consider air to be a gaseous solution, then everything is in a gaseous form. That is a solution. That's what we mean by homogeneous. Homogeneous mixture that makes up the solution, then we have two components, and the first of these components we call the solvent. And usually, by definition, the solvent is merely the component of the mixture in the greatest amount. We could talk about it as being the material dissolving or the material being dissolved, but that gets us into difficulty sometimes when we're talking about solutions made up of, say, two liquids. Which is dissolving in which. So rather than define it that way, we will merely define the solvent as being the component in the greatest amount, and the solute the component or components of the mixture being in the lesser amount. Now, most of the solutions we're going to be looking at and dealing with are going to involve water as the solvent. And any time we're working with water solutions, then we are talking about aqueous solutions. So when water is the solvent, then we are going to be saying that we are talking about aqueous solutions. And so I've indicated here, here's a solute X, whatever that is, and it's dissolved in water, and so in a chemical equation, then we would show it as X with a little subscript AQ. That identifies to the reader then that we are talking about a water solution of component X of the solute. All right? And as I say, water is one of our most common solvents, and so we will be dealing primarily with water solutions. Now, obviously, if we do have homogeneous mixtures, we probably also have heterogeneous mixture. A heterogeneous mixture is not a true solution. A heterogeneous mixture is called a suspension. For instance, if we have dirt particles in the air, they are solid. They are suspended in the air, making up then not a solution, but in that case a suspension of dirt particles in air. Or if you were to look at a sample of, say, the Mississippi River water, you would notice that it's cloudy appearing. It's cloudy because it is a suspension of small little dirt and clay particles in the water. It is not a solution. It is a suspension. One of the characteristics, or one of the ways that we can tell the difference between a true solution and a suspension, is what we refer to as the Tyndall effect. If we have particles that are not homogeneous, they tend to scatter light. And if they scatter light, we can actually see a light beam passing through a suspension. We cannot see a light beam passing through a solution. And the Tyndall effect, there's one shown in the text dealing with droplets of water, liquid water, in air. Air itself is a solution, but if we have droplets of water in the air, it then becomes a suspension. And if we were to look at a lighthouse, for instance, and we see the beam of light, we see the beam of light not because of the air suspension, we see the beam of light as it is scattered off of the suspended particles rather than the gaseous particles making up the solution. Or if you walked into, say, an old dusty building on a sunny day, you might see a light beam coming in. If the air is clear, as it would be in here, if we had sunlight coming through an opening, we probably would not see a beam. But if we have a lot of dust suspended in the air, you'll see the beam of light as it passes through the suspension. Or if you go out on a night and you see the spotlights going up into the sky, somebody's advertising opening a new car dealership or whatever the case might be, that beam of light that you see, you only see because it is striking then a suspension. It's striking water droplets in a cloud. If it was a totally clear air, no moisture, no droplets, no clouds, no dust, you would not see those advertising lights. They have to have something that's suspended to bounce the light off so that we would see them. So, the key difference once again then between a suspension and a true solution is whether they are homogeneous and don't scatter light or heterogeneous and do scatter light. Let's take a little look at the dynamics involved in preparing solutions. And this time we're going to focus now on solutions involving water because, as I said, the majority of the solutions we will be dealing with really are aqueous solutions. We start by placing a block of solute into the solvent. And in this particular diagram here, the solvent molecules are indicated here as dark colored, and the solute molecules as just being empty circles. Now, when we first put the solute into the beaker, then the only thing that is there are solvent molecules out here, and of course the solute molecules making up the chunk of solid that we have put in. Now, the solvent molecules are in constant motion. Anything that has temperature has motion to it. And so these solvent molecules are flying around at fairly high speeds, actually, and they are colliding with this solute that we put in there. Now, occasionally, enough energy will be transferred. Kinetic energy from the standpoint of the particles moving. So the solvent here is providing kinetic energy. Part of the kinetic energy may be transferred to a solute particle on the surface. And if that solute particle gains enough energy, it may actually be able to overcome the attractive forces of the other particles and move into solution. So it is an energy transfer process that is occurring as this process occurs. And this process of a solute molecule absorbing energy and becoming dispersed in the solvent is identified as dissolving. That's the term that we use for it. However, after some length of time, and we have now allowed considerable number of dissolved particles to get into solution. Notice that this beaker, as compared to this one, shows a lot of the solute particles now in solution. If a solute particle, let's focus right here now, if a solute particle that was now previously dissolved collides with the surface of the remaining solute, solid, it might lose some of its energy. And if it does lose some of its energy, it may actually stick. It may actually become reattracted back to the undissolved solid. So it is an undissolving process. But the term that we use for the undissolving process, where solute particles are going back out of solution, is referred to as precipitation. When we initially put the solute in, the only process that can occur is dissolving. After some length of time, however, once we have particles dissolved, we can now begin to get the process of precipitation. Now, if we put in enough solute, what will happen is that we will reach a point along the way where the rate of dissolving will become equal to the rate of precipitation. Whoops, end of the paper there. Rate of precipitation. In other words, we're going to reach a point where the molecules of solute that are leaving the surface have become equal to the rate at which they're going back out of the solution. And so after that point is reached, then basically no more solute would appear to be dissolving. We've reached the maximum sweetness. We have reached the maximum color intensity. We've reached whatever maximum property we're going to have at that point. And this particular condition here is referred to as a dynamic, meaning that it's continuous, occurring, equilibrium. Dynamic equilibrium, and of course the term equal would imply two things that have become matched, and so the equilibrium is the fact that these two rates have become equal, but they don't stop, and that's one of the key things. It is not a static equilibrium, it is a dynamic equilibrium. For instance, if I walk over here and put my hand on the wall and lean on it, I am pushing against the wall is pushing against me, and we are doing so in an equal fashion. If not, I would collapse through the wall or the wall would collapse on me. This is called static equilibrium. Nothing is happening between the wall and I at this point. We're both exerting an equal force. But the difference here is that in dynamic equilibrium, the dissolving process is still going on, and the precipitation process is still going on. In other words, there would be different particles in solution at different times, but because the two rates have become equal, we would not be able to detect any difference in the property of the solution. It would have reached a certain then concentration of the solute, and it would now be a constant concentration, but it doesn't mean that the process is stopped. The processes continue to occur. Well, when we reach this condition for a dissolving process, then when dynamic equilibrium is reached, and by the way, each of those equilibriums are dependent upon a temperature. So in other words, if we change the temperature, we would change the dynamic equilibrium until it is reestablished. But once we have reached dynamic equilibrium and the rate of dissolving has become equal to the rate of precipitation, we say that the solution has become saturated. It has the maximum amount of solute in it at that particular set of conditions: temperature, pressure. A saturated solution has the maximum amount of solute dissolved at those set of conditions. All right? And of course, as I say, it doesn't mean that dissolving is stopped. It only means that dissolving and precipitation have become equal. Well, that's one way we could qualitatively, at least, talk about the amount of solute in a solution. We could talk about the solution is saturated. But that really doesn't tell us much, because a saturated solution of sugar at, let's say, 25 Celsius degrees versus a saturated solution of sodium chloride, table salt, at 25 degrees doesn't have the same amount of solute in it. It is saturated for that particular substance, but it doesn't mean that it's the same amount. So it's not very quantitative. It's only qualitative for that one particular system. Well, of course, a couple of other terms that we use then if we haven't reached that condition. A good example, let's suppose we take a cup of hot water or tea, and we put in a teaspoon of sugar, and we stir it, and all of the sugar dissolves. We haven't reached an equilibrium. There's no undissolved solute there. So the tea has not become saturated with the sugar. But if I scoop in maybe another 15 teaspoons and then stir it, I finally reach a point where no more solid sugar dissolves, or it appears that it's not dissolving. Now I have reached a saturated solution. And so the term unsaturated really, again, doesn't mean a whole lot. It just means we don't have the maximum amount. It means we could have from one molecule to a truckload, depending upon the material and the size system that we're dumping it in. It only means that we have not reached the condition where the system has become saturated. Now, another term that we do use is supersaturated. The term supersaturated actually implies that we have more dissolved solute than is allowed. And you might say, well, how can we have more dissolved solute than is allowed? Well, if we prepare a saturated solution at an elevated temperature, so we make a hot solution and we make it saturated, and then we very, very carefully cool the system down, we may actually be able to get the system to hold more solute than it theoretically should be able to. In other words, you cannot make a supersaturated solution up directly. You must make up a saturated solution at an elevated temperature and carefully cool the system off. Then it could become supersaturated. And supersaturated solutions are very unstable. It usually doesn't take a whole lot to immediately get them to begin to precipitate out all of the excess solute. There are a couple of pictures in the book demonstrating this, and in the next lecture I will try to demonstrate that as well. But supersaturated just means then that we theoretically have more solute in there than we should really be able to have. Now, two other terms that we use relative to the amount of solute in a solution. Again, these are rather quantitative terms. We talk about concentrated. For instance, if I were to go up to the lab, I might find a bottle labeled concentrated sulfuric acid. Or I might find a bottle that says dilute sulfuric acid. And so it really doesn't tell us anything that quantitative again. Concentrated just means that it has quite a bit. And so typically we're talking about solutions usually above what we call 10 molar in concentration. Dilute means that it's less than that. It could be 5, it could be 1, it could be a tenth, it could be 10 to the minus 5. All dilute means is less than the concentrated is. All right? Now, concentrated does not necessarily mean the same as saturated. They might or they might not mean exactly the same. But both have the same general idea that we have a lot of solute present in the solution under those conditions. And as I say, the concentrated may not truly imply that we have reached a saturated or a dynamic equilibrium, but we have near the maximum solute in the system when it is concentrated. Now, when we carry out this dissolving process, we looked at the dissolving process. When we carry out the dissolving process, of course, the material that's being dissolved may actually go into solution in two different forms. Recall, when we talked about matter in Chapter 1, we said matter could exist as atoms or molecules or charged particles that we called ions. When we dissolve a solute, it may go in as an atom. For instance, if we were talking about helium as part of a gas mixture, the helium would be as helium atoms. So it's dissolved in the form of atoms. Or we can talk about it as molecules. The nitrogen and the oxygen in our gaseous solution, called air, is in the form of molecules. Or if we dissolve some things in water, they go in as molecules, neutral particles. But sometimes when we dissolve materials, they go in as charged particles called ions. And of course we have two types of ions, those with a positive charge and those with a negative charge. The positive charged ones we referred to as cation ions, and the negative charged ions are referred to as anions. Well, we can actually carry out a test to determine in what form a solute is going into solution. And we can do this by carrying out what we call an electrical conductivity test. If, when we put a solute into water, it goes in as a molecule, we find that it will not conduct an electric current. And so molecular solute, meaning it dissolves as molecules, then are called non-electrolytes, meaning it will not conduct an electric current when we put it into solution. Ionic solute will conduct an electric current, and we refer to that as an electrolyte. And we can even differentiate in electrolytes. We can have those that we would call weak electrolytes, meaning that maybe some of the material going in goes as a molecule, some of it dissolves as ions, and so we can have a weak electrolyte. Or we can have something that 100% dissolves as ions, and we refer to that as a strong electrolyte. So we can then carry out measurements to show what form a solute really is moving into solution as. And we'll take a moment here then and take a look at a little demonstration dealing with electrolytes and non-electrolytes. I have set up here an apparatus which will allow us to measure electrical current passing through a solution. That's this little box here. And on top it says danger high voltage. That's because I'm going to plug it into the outlet. So it means that these two little prongs here, make sure it's not plugged in, these two little prongs here are going to be at 110 volts. So if I were to grab these two like this, my eyes would probably light up, and I would of course jump around a little bit. It'd be like sticking your fingers into the socket. All right, so this is what we're going to use as the measuring device. And to kind of take a little bit of protection, I'll take off any jewelry because of course metals are excellent electrical conductors, and so I don't want to accidentally teach that or touch that on a ring. Do we have anybody that knows CPR? Some, okay. All right. I would hope that you would use it if I do make a mistake and accidentally grab those tongs. Kind of in joking, but it isn't, because accidents do happen. We would hope that it wouldn't, but in case it did, it's nice to know at least somebody has some general idea of how to take care of me. All right? Now, we're going to start then, and I'm hoping that we can see with all the lights on. If not, I may have to turn the lights down just a bit. And I'm going to go ahead then and plug this in. And the first thing I have here is a beaker of water. This is pure water, and if I place it now here, you notice that nothing happens. The light bulb does not come on. And of course that doesn't really prove a whole lot, because maybe the light bulb didn't work in the first place. So maybe I didn't prove anything. So we'd have to know in fact that the light bulb did work. Well, one way of course would be for me to take the wire and squeeze it and touch it together, which would close the circuit and the light bulb would work. But instead of doing that, I have a beaker here which I just filled before class with Springfield tap water. All right? So we'll test it, and we notice that the light bulb comes on. If the light bulb comes on, it indicates that there are ions present, and we see that it comes on quite brightly, as a matter of fact, and so therefore it does contain dissolved solute in the form of ions. Once again, if I go back to the water, nothing happens. And if I look at the regular water here, we see that in fact it does conduct. If we were taking a bath in pure water, we really wouldn't have to worry too much about the conductivity of the water. But unfortunately, most of us do not take baths in doubly deionized water at about $3 a gallon. So most of us do use regular water, and of course that does conduct an electric current, and if you were in there and turned on a light or hit something that was an open wire, obviously you become part of the conducting system. The next thing I'm going to do is I'm going to take, again, some doubly deionized water. We see nothing happens as far as the conductivity, and we will take a packet of sugar, dump the packet of sugar in, stir it up a little bit, and we will test it, and we see nothing happens to the light bulb, and therefore it would indicate that sugar, when it dissolves, goes in as the form of neutral molecules. You might say, well, maybe yes, maybe no, because by now maybe the light bulb burned out, and so we better check. No, the light bulb's still working, and so therefore we know that in fact the sugar does not conduct. It's dissolving as a molecule. Take another beaker here, test it. We see nothing happening. This time I have a little bit of table salt here, sodium chloride. And it's caked just a little bit. I'll tap just a little bit in there. I won't even get carried away like I did with the sugar. And we'll test it. And you notice I barely have to touch the electrodes and the light is on. It's just almost like a switch. Fully bright light bulb. In other words, sodium chloride is a strong electrolyte. When it dissolves, it's almost 100% sodium ions and chloride ions. Sodium plus and chloride minus ions in solution. And so we would classify then table salt as a strong electrolyte. We'll rinse those electrodes off a little bit. This is, of course, one of the other places I have to be a little concerned. If I spray water across and hit my finger, that can give a little jolt. All right. Let's look at something here that we use in the lab. Hydrochloric acid. 6 molar hydrochloric acid. For those doing laboratory work, as a matter of fact, we'll be using it in this week's experiment. So let's see how it behaves. First of all, we check the solvent, the water, nothing is happening. And I'll take this then and add a drop or two. That was 2 drops. 3, 4 drops. And notice that immediately it began conducting. Hydrochloric acid, HCl, is a strong electrolyte. It's 100% ionized in water to H plus ions and Cl minus ions. Now, I'll take another acid. Again, we'll check the solvent first. And this is an acid that you would have in your home, vinegar. And we'll test it. And so we saw that with the HCl, a couple of drops turned the light bulb on. We'll try to hit a couple of drops here so we can make a comparison. Well, most of it went on the floor, but we got some in. Notice that nothing seems to be happening yet. Whoops. And with about 10 times as much in there, you might be able to note that the filament of the light bulb is just barely glowing. Now what that means is that, yes, some of the acetic acid, some of the vinegar that we put in is ionizing, is going in as ions, but apparently most of it is going in as molecules. So we classify then vinegar, or acetic acid as its chemical name is, as a weak electrolyte, all right? So it does conduct a little bit, but it certainly doesn't conduct as much as the hydrochloric acid. Remember, that only had like 3 drops in it. And the vinegar, even though I missed a little bit, probably has 15 drops in it or more. So much more acid and yet much less conductivity. All right, let's look at 2 compounds that we classify as bases. As a matter of fact, in Chapter 5, our next chapter coming up, we're going to talk about acids and bases. As a matter of fact, we're going to talk about strong acids and weak acids. And when we talk about that, we're going to talk about their ionization. And the ionization will go back to this conductivity to talk about that. Bases can also be strong bases and weak bases. And so let's take a look at a couple of those. Here I have, we'll just rinse the electrodes off again quickly. Here I have sodium hydroxide, NaOH. Sodium hydroxide is classified as a base. And we'll put it up there and we'll try to add a drop or 2 of the sodium hydroxide. Well, I thought I would add a drop or 2. Oh, there we go. That was 6 drops, and we notice the light came on quite brightly if I get this stirred up a little bit. 6 drops of the 6 molar sodium hydroxide, the bulb lit brightly. It means that almost all of the sodium hydroxide is going in as sodium plus ions and OH minus ions. We would classify sodium hydroxide as a strong electrolyte. All right? Plain water. And this time we'll take a chemical that you probably have around your home, although this one's a little more concentrated than that. This would be like Windex. Ammonia, aqueous ammonia, solutions of ammonia are good window cleaners, glass cleaners. And so we'll test that. Ammonia is also called a base. So we'll take a little bit of it and we'll try to add a drop or 2 again as we did with the other one. And I think I put in as much. I don't see anything happening. We'll put in a little more. And by adding considerable more, we finally got the light to begin to glow, the filament. Not very bright, however. And so again, this particular compound would be categorized then as a weak electrolyte. All right? And finally then, we might ask, what about ethyl alcohol? In this chapter, we're going to talk about two other solvents, two other organic compounds that act as solvents. One are the alcohol group, and the other is the ether group. Both are organic compounds, act as solvents like water does. They're liquid solvents, but they have different characteristics than water. But what we might wonder, what happens to ethyl alcohol when we dissolve it in water? Well, let's see. We'll need, I guess I brought one too few beakers, so we'll dump this one out, which was just the tap water, and we'll rinse it one time just to make sure that we get rid of the city ions. Now, the ions in tap water are from ions or compounds that we say make the water hard. Calcium ions and magnesium ions are the two that are in there. And that's what makes water hard. That's what makes water then form a solid material when you heat it up in a pan and you get the white precipitate or the white scum. It's the ions that react with soap and make an insoluble soap scum. That's the hardness. Calcium ion and magnesium ion. All right, we'll check first of all, and nothing is happening. And then we might say, well, we better double check the light bulb, and we'll do that. And it's still working. And now we'll take a little bit of the ethyl alcohol, and we'll dump some of it in. And we'll check it, and we notice that nothing happens. Ethyl alcohol must go in as a molecule, a neutral dissolved species. And so we would say ethyl alcohol, C2H5OH, chemical formula, is then a non-electrolyte. So we can use this form of experimentation to actually determine what happens to a chemical when we dissolve it. And that's important to know when we're carrying out tests or chemical reactions, because the way we write a chemical equation really needs to reflect the actual form of the species in there. In the laboratory work that those of you in Chemistry 105 will be doing in experiment number 5, you're going to be needing to write some equations, and you need to show exactly the form that the material is in. For instance, we might say sodium hydroxide reacts with hydrochloric acid to form water and sodium chloride. And we're going to write then the chemical equation for this. Now, sodium hydroxide, I should have said sodium hydroxide solution here, and hydrochloric acid solution, so that we know that. Now, sodium hydroxide we just tested, and it conducted an electric current, meaning that actually sodium hydroxide, chemical formula NaOH, we'll write it first in molecular form, plus HCl aqueous, that's hydrochloric acid, then forms the products of water, H2O, and sodium chloride aqueous, solution of sodium chloride. Now let's think about this. When we tested the sodium hydroxide, if you wrote it down, we found that sodium hydroxide was a strong electrolyte. So it's actually not sodium hydroxide molecules, it's actually a sodium ion, aqueous, and a hydroxide ion, aqueous. That's the way it really is in solution. Hydrochloric acid. When we measured the hydrochloric acid, you might have jotted down an observation. It was what? Strong electrolyte, conducted an electric current brightly. So that means that hydrochloric acid is actually hydrogen aqueous ions and chloride minus ions. When we tested the conductivity of pure water, what did we find out? Does pure water conduct an electric current? No. Therefore, it must be a molecule. It must not contain any ions. And so therefore, water should be written as a molecule. And we would show a little L because water is liquid state when we're talking about solutions. And finally, sodium chloride. Remember, we started with sugar, nothing happened. We added a little bit of sodium chloride, table salt, and what happened when we did that? Conducted an electric current, meaning that sodium chloride in solution then is not sodium chloride molecules, but sodium plus ions and Cl minus ions. Running out of space, I should have turned it sideways. That's the actual way that the chemical reactants exist and the actual way that the chemical products exist. So by measuring then the behavior of solutions, one can more accurately depict the way that chemical reactions really look. As a matter of fact, if we look at this carefully, we notice that we have a sodium ion on this side and a sodium ion on that side. Is there any difference in those? No, and they're both in the same beaker. How would we know which was which? We would have no idea at all. In other words, the sodium ion really hasn't changed at all when I dumped these two chemicals together. It was a sodium aqueous ion when I started. It is a sodium aqueous ion when I finished up. And we would say then that the sodium really hasn't even reacted. It didn't chemically change. All right? As a matter of fact, the term that we sometimes use when we write equations where we take out ions that aren't involved, we refer to these as spectator ions. Okay? Sodium ion is a spectator ion. It saw a reaction occur, but it's not involved. We look here, is the hydroxide the same on both sides? No. We don't even see any hydroxide over here, so apparently it has changed. Hydrogen ion, don't see any hydrogen ion over there, so it has changed. Chloride ion, looks the same on both sides, doesn't it? And so right there then is another spectator ion. If we get rid of the spectator ions, we could write this chemical equation as OH minus aqueous is actually reacting with H plus aqueous to produce H2O. That is, in fact, what the chemical reaction was if we dump those two together. That's sometimes referred to as the net ionic equation. The net ionic equation. Now, of course, the term net means that we're only including then that is above and beyond what we started with. If we were investing, we have a net gain or a net loss. The difference between where we are today versus what it was or where we were when we first invested. And if we're talking about this, this is the net change. Only the hydroxide and the hydrogen ion have actually undergone a chemical change. Well, tomorrow, or in our next lecture, then, we will come back to take a look once again at the idea of the amount of solute present in a solution. We talked about these two terms, which are not very quantitative, and we'll begin by looking at a quantitative description of the amount of solute in solution by looking at percent by mass composition of chemical solutions, and we'll take that up in our next lecture.